Cambridge. I'm going to talk about the use of scan statistic for multiple change point inference in time series. So scan statistic is a rather well-developed thing, and but when I start working on this problem, I mostly found people use the scan statistic for testing of change point, but not that often used for estimation. Until yesterday, we saw two very excellent talk about the binary segmentation and the log periodogram, which is also kind of using the scan statistic idea, using local window for estimation of change point. And so in this talk is also talking about similar ideas, but I'm more focusing on the computational complexity aspect, and I hope I wouldn't bore you. So I'll start with more motivation about why using scan statistic for estimation change point is good. So first, look at these three, which is the pointer. Okay, so there are 3 time series, and it's pretty easy to use eyeball to see change point is here, here, and here. What's special is that these 3 time series is actually the same time series. So this part is just the middle part of the first series, and this part is the middle part of the second time series. So what I want to say is that when I'm going to detect a change point, I just zoom in closer and closer, and until a range where you feel comfortable and you see, oh, the change point is here. In fact, so for this time series, you just use the very middle part to locate the change point, and the rest are not important at all. So in the literature, most of the time we see the asymptotic result is that the tau hat and the tau zero, the estimated and the true change point, is of order big O1. So the asymptotic is that before change point and after change point we have growing observation. So it means that no matter how many time series you have before and after the change point, you still make the same order of mistake. So the rest are not important. Only the middle part is important. So to locate a change point, we don't really need too many data. And so if you want more concrete example, let's see this one. Before 100 is white noise, and after 100 as a mean change, I observe 200 observations. And what I do is that I take the middle 20 observation, middle 40 observation, etc., and I do the cum sum statistic to find the estimation of change point location. So what I'm doing is that for each time series, I have 10 subsamples, okay, middle 20, middle 40, etc. So it is the same time series, but partitioned into 10 parts. And so I do the cum sum for the location of the change point. I do this 100 times, and I found that in this 100 times, 80 times, so for each time series, I have 10 estimates of change point. So in this 100 time series, I get 80 times of them, the 10 taus estimated change point are exactly the same. And even though there are 20 times that they are not all the same, the standard deviation of that 10 standard deviation, 10 estimated change point is only 3, which is very small. So this motivates. We only need to use a very local data to locate the change point if you are going to estimate the change point. Okay, so some very basic scan statistic, and the scan statistic is kind of used in testing problem, and until yesterday I found the scan idea was actually used for estimation. And so today what I want to use is a likelihood ratio scan statistic that allows consistent estimation for multiple change point in time series, and I will also construct confidence interval using that scan statistic. And it is fast and very easy to implement. So it will be a 3-step procedure. For the first step, I will use the scan statistic to locate the change point. and to detect the change point. And then after that, in the first step, the change point that we locate will be an overestimated set, will be overestimated. The number of change points will be overestimated. And the second step, I will use a model selection approach to consistently get the change points. And then finally, I will construct the confidence interval. And so the setting is that I work on piecewise stationary time series. Our observation is x, and the change points are tau, and each piece is the y. We assume piece y AR. And so I also define the lambda as the rescaled change point. And so this theta is the AR order. And so the first step is that I use the likelihood ratio scan statistic. So this S is the scan statistic I define. So on the top is that the likelihood when you assume there is a change point. Okay, so you have two parts. And at the bottom is that you assume no change point. So this likelihood ratio will be big if you have a change point at t. So so first I have to select the window. Okay, so this is the only tuning parameter we need in this whole procedure. I need the h such that the minimum distance. It should be tau, not the lambda. So it's the actual length. So that the window I use will only have at most one change point inside. So I use the window to scan it, and then I have this scan statistic. So in fact this likelihood can be more general, just because it's my first attempt. When I prove something, I need some sharper rate of large deviation inequality. So I have to work on the AR model first. But I guess it's possible to generalize to more general situations. So if we assume AR model is kind of I have a very simple expression for the scan statistic. And what I'm going to do with the scan statistic, because I know that the window I have, which is of length 2h, will have at most one change point. So I look at the scan statistic. For each time point, I look around the neighborhood of 2h. If it is the maximum over the 2h neighborhood, then I think that it may be a potential candidate for a change point. So I do this. So usually it will be the local minimum. Okay. So these few local minimum, these blue dots, are called the local change point estimate, which is the product of my first step. Okay, I use the scan statistic to detect the possible change point, which are here. So what I can prove is that if h is bigger than d log n, which is not very large, then I have this kind of consistent property where for each true change point I can find one tau hat 1. So usually because I have a 3-step procedure, so when you see bracket 1, bracket 2, bracket 3, it is the product of the 3-step. Okay, so for the first step I found a change point, so there is one change point close to the true change point in the h neighborhood. Okay, so it means that for each change point I have one estimated change point around it, but it may be overestimated. Okay, so what can we do if it is overestimated? We can use the second step, which is a model selection approach, to reduce the set to have a consistent estimate of change points. So traditionally, people use some information criterion, for example, AIC, BIC, or the MDL, to do a model selection type approach to find the change point. So what they do is that they have the information criterion, which relates to the number of change point. This L is the location of the change point, and this P is the order of the AR process. Okay, so it's a vector of AR order for each piece, and so it consider the minimization over all the n observations, so it is computationally infeasible. But using my first result, because for every change point I have an estimated change point close to it, so if we reduce the minimization domain from all the observations to the first step, the set estimated location in the first step, it becomes computationally feasible. Okay, so and I will talk more about in later about the implement of this. And so what I can prove is that in a general information criterion like the log likelihood function plus some penalty, if the penalty is less than n order and bigger than log n order, then I have consistent estimation in the sense that this M2 is the number of estimated change point for the second step, which is minimization of this information criterion, and is consistent, and also the location is close in the sense that the true and the estimated change point is within h distance, and also AR order can be consistently estimated. Okay. However, this is an h, but not a constant. Okay. So it means that there's no guarantee that the tau hat 2 minus the tau hat is big O1, which is the traditional result. So in fact, but we know that the true one is within the h neighborhood of the tau hat 2. So we can do some improvement by introducing the extended local window to have a consistent, to improve the estimation. So now we know that the true is within h neighborhood. And so what we can do is that we introduce the extended local window. So with not just minus and plus h, minus 2h and plus 2h. So what we can do is that with the extended local window, I can have this true value which is within the middle part of this extended local window. And what I have is that the number of observations before and after tau will be going to 0, and also this extended local window only contain one true value. And so we can do the estimation again on this extended local window. Okay, just like I have the observation on the extended local window, and I applied the search for one change point. Okay, if I do this updated change point will be the final estimate, and I can show that this is big O1, which is the same as the traditional result. And also using the extended local window, we can borrow the idea of length, which derives the asymptotic distribution for the estimated change point if you have only one change point, and in a very general context of time series model. And I have the distribution like this, and but this distribution is kind of depends on the theta 1 and theta 2, which is the model. So it's not easy to use in practice. I'm not sure a bootstrap method can be done because it's kind of non-standard problem. So they developed a approximation to this WK. And so finally, what you can do is that to apply this very easy formula, you can have you can construct confidence interval. Okay, basically. So just a quick look at the computational capacity. So we have 3-step: detection, model selection, and construction of confidence interval. For the first step, I use a scanning window to detect all the change points. So I need only h capacity for computing one scan statistic, and I scan it, so I'm doing this n minus 2h time, so and add together is just nh order. And the second step for the model selection procedure, because the domain of selection is just m hat 1, the first step, the number of estimates in the first step. So using kind of dynamic programming, I only need this square times n. N is for calculating the likelihood to do the computation. So if you think that m1 hat is too large, then you can notice that what are the bulldogs, the first step estimates, is that if you have a change point, I will have a large value, but I will have some local maximum, which are kind of false positive thing, which are kind of smaller, but if you use first sorting, it's kind of still difficult to design a first sort. Okay, sometimes you may make mistake, but model selection approach has the advantage of that you can take those out, and then model selection approach will give you consistent results anyway. So so what we can simplify is that we sort this scan statistic and take the say b greatest value. Let's say I assume my time series has only maximum 20 points, so I take b equals to 20, and then you just this is bounded by 20 squared, so it's fast. And the final estimation of change point will be of order x squared, which is kind of a small portion of the first two steps. So the final total computational capacity is only nh. So because h, when if you remember the first theorem, if h is bigger than d log n, okay, d log n, it will be okay. So the h is of order log n. So the computational capacity is n log n, which is fast. And so so I do some simulation studies. So first, the most important thing is that I have only one tuning parameter, which is the window length, which is a d log n. So so d is actually the same as the n. So I choose how to choose the d, and I found that the choice of d is not that important. It's quite robust. And so here, this sensitivity analysis is giving us some idea about how to choose the d. So how does the d affect the first stage estimation, and how does the d affect the estimation results? So we work on this model, a piecewise AR, and so n is equal to 1024, and replication is 100. So this is the d. I try a lot of d. Okay, so if I specify the d log n is the h, is the window size, the size of the window of scanning it, and then after scan it, I get the set, and then use model selection approach to get the final estimate. And so m hat 2 is the result from the second step, which, because we have two change points, so this is the correct number of estimation. So is 98 or above. Okay, for most of the range, I get the correct decision of the number of change points. Okay, so so this tau hat 2 minus tau hat less than h is that remember that in step 3, what I relies on is that the true is inside the h neighborhood of the second estimate, and then so that when I use the extended local window, the tau is in between, so that I can have the consistent result. So you see, over a large range of the d, I also have very high disk coverage, so that when I use the extended local window, the performance should be okay. And you see the FHMDL it doesn't change much. It's 101 something. and the time is also fast. And so the conclusion is that the choice of H or D is not that relevant. If it is small enough, you will have the consistent estimation. And so what you can notice is that if the H is too large, so you see here, my length is 1,000, and here, so the minimum segment is from 0.5 to 0.75 of 1,000 is about 250. And so it's just that when the H is bigger than 250, I have a sudden change, okay? So from 52 to 3 for the correct estimation, and my MDL increased suddenly from 101 something to 104 something. So in practice, we can if we want to choose a very good H, we can try a lot of H, increase it until that MDL increase a lot. Then we know that we should stop, and then we can choose the H. And in most of the case, not just this time series, in other cases, I found that H from 50 to 100 works very well in most cases. So let's see other simulation example. So I just this is the same as the previous, but I'm more closely looking at the estimation of the location of the change point, and I'm also make comparison with the AutoPalm and the PELT, which is the POM dynamic programming. So you see the tau, the estimation of tau are all very good for all three cases, and but my standard deviation is even smaller than the AutoPalm, and coverage is similar, although we are a little bit worse in this case, but in the next slides we are better, and so the time is much faster. So for PELT, it is exact linear time when you have the number of change point is going with the number of observations. So in this case, we have long time series, but only 2 change points. It can be very slow, but PELT is the exact minimization. So the accuracy should be better than us, but it is too slow. So I only use 5 replication here. So, and for second time series, it's not actually AR. So it's armor changed to AR changed to MA, and so in this case, our coverage, which is the number of estimation, the correct number of estimation of change point is all 100. And for AutoPalm, when n is large, the performance becomes worse than us, because AutoPalm, it is using the genetic algorithm, which is kind of a educated try and error. It throws some chromosome to estimate it. But if n is large, you have to throw more chromosomes. So if you use the same numbers of chromosomes, you may not get the very accurate result. But the time is much smaller. So maybe I skip that and only mention the example of real data. This is also EEG data, and this data set is provided by Umbo, so he's appearing again. So this data set has 30,000 observations, and so we applied our 3-step procedures, AutoPalm and the PELT, and our procedure found that the minimized MDL is 4195, which is smaller than the AutoPalm, and the numbers of estimator are similar, and we only take 400 seconds. AutoPalm is 1 hour, a little bit more than 1 hour, and the PELT took me more than 1 week, but it has really smaller MDL, but comparing the difference is not that large. Okay, so we are doing a good job, and so this is the estimated location of change point. So you see, this is AutoPalm, and this is the three-step procedure. We have the green thing because we can also provide the confidence interval, while the first two are just the location of change point. And so compare us and the AutoPalm, the location of the change point are quite similar, but I'm not sure why if when I use the pelt, it has more location here, and but luckily there are more change points. If these change points are not there, it may take me longer to run the program, and it is kind of interesting to look at this area. So for this area, you have a lot of green thing. In fact, for each red line, it is associated with a green band for the confidence interval. It's just that some green band is too narrow and you don't see it. For this one, the green band is large, means that the confidence interval is large, and you see there are many red lines around here. It means that you may detect a lot of change point, and here it says the change point is not so clear. So maybe it is a sign of local stationary. Maybe in this range, you can fit a local stationary model rather than a change point model. It suits better. So or maybe so this is another example. Just demonstrate how to construct the change point, and the change point means something in the return. And so conclusion, I introduced a three-step procedure for inference in change points. So first, I use scan statistic to detect the change point. Next, I estimate by model selection procedure, and then finally, I construct the confidence interval. And it is fast, with few non-sensitive tuning parameters, and expressively suitable for large N and small m, few change point case. Okay, thank you very much.
Well, I would like to make a general comment that goes beyond your piece of work, which is certainly a nice piece of work. It's more like encouraging all of us to use data sets with a little bit of background, what these data sets could be used for. So let me be a little bit more precise. I'm a little bit surprised that we take, say, this ECG data or EEG data and compare just a couple methods to see whether we get 12, 15, 33, whatever breakpoints. Now, I was kind of responsible with Hernando to have had a look on the physiological meaning of these data sets. It's basically about onset and offset of epileptic seizure. So basically what people are interested in is to find where there could be a first breakpoint, which we clearly see here. And then all the rest, okay, it's not so clear whether it's of interest. Maybe the offset or maybe two more or three. So what I'm trying to promote here is a little bit, we need to probably fine-tune all of our methods and competitors with this background information. And we had heard earlier this week that it matters a lot whether, for example, with PELT, we use the default penalization method or a different one, and that actually has a lot to do where the data comes from and what the nature of the data is. I mean, clearly this data set is very different than, say, a change in the mean in a regression function, right, with the IID errors. So, I mean, I would just like to encourage all of us to be a little bit more careful, because if you have a look on this, somebody who's not in the field, 33 points found by PELT, it doesn't fit with the nature of the data at all. That's a general comment that I want to make. So, I don't know.
Any other questions? Let's thank the speaker and move to the third talk.